Alright, so today we will be looking at covalent bonding, naming, and formula writing. So, after this lesson, you will be able to name and write formulas of covalent compounds using the IUPAC nomenclature rules. So, covalent compounds are a compound that contains a not or a non-metal atoms held together by a covalent bond, also known as molecular compound. Covalent compounds do not contain any ions. Instead, the atoms are held together by covalent bonds, which are two atoms that share electrons. Molecular formulas show the exact number of atoms of each element in a molecule. Therefore, the atoms in a molecular formula do not always display the lowest whole number ratio like in ionic compounds. An example of this would be dihydrogen dioxide, is commonly known as hydrogen peroxide. Right? So we can see the hydrogen peroxide molecule down at the bottom. H2O, like water, is dihydrogen monoxide, right? You have two hydrogens, one oxygen. So, covalent bonds are formed between metals due to a reactively small difference in electronegativity. Not metals or nonmetals include nonmetals and metalloids. All not metals have relatively high electronegativities, so their electronegativity difference is less than or equal to 1.7. Right, we remember that ionic bonds are above 1.7, while covalent bonds are below 1.7. So a very small difference in electronegativity, less than 0.4, results in a non-polar covalent bond where electrons are shared equally. Electronegativity differences greater than 0.4, but not enough to create ions, result in a polar compound where electrons are shared unequally. So, in a non-polar bond, they are in a straight line, and in a polar bond, one is going to be on the top, and the other two are going to kind of be at the bottom. One has a stronger pull of electrons than the other ones do. Now that we know what covalent compounds are, let's learn how to name them. Covalent compounds are named using Greek prefixes to be specific exactly how many atoms of each element are present in the compound. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. I will give you a table on the test for you to look at, and you also have a copy of that in your notes. Binary molecules compounds are covalent compounds that consist of two non-metallic elements. Binary molecular compounds are named using the following pattern. The prefix that indicates the number of the element of the first element plus the non-metal name, then the prefix of the number of the second element plus the second non-metal name plus IDE, just like when naming ionic compounds. The most electronegative goes second, and then we put the prefix on the name of the first element if there are more than one. So if there is one, we don't put mono on the first element, but if we have two of the first element, we will put the name. So an example of this rule would be SF6. So we have sulfur hexafluoride. We can see sulfur is the most electronegative because it's closer to the top right corner. So sulfur goes first and then fluoride. Fluoride is the most electronegative, so it goes second. Since the prefix in the name of binary molecular compounds denote the number of atoms of each element in the compound, the formula of these compounds are simple to write. The number of the atom will be the subscript in the formula. Remember that if there is no prefix on the first element name, that means that there is one atom of each element, of the element in the molecule. For example, the binary molecule compound nitrogen dioxide. Nitrogen does not have a prefix on it. There is only one atom of nitrogen in the molecule. The prefix di in the word dioxide indicates that there are two atoms of oxygen in the molecule, so the formula will be NO2. The formulas are written from least to most electronegative. So oxygen is more electronegative than nitrogen, so nitrogen goes first. All right. You should now be able to name and write formulas, covalent compounds using IUPAC nomenclature rules. You should also be able to construct an argument to support how periodic trends, such as electronegativity, can predict bonding between elements. Let's look at some practice problems together. What is the name of P? Phosphorus. We have two of them, so we need to make sure that our name at the beginning of phosphorus, our Greek prefix, is correct. So I have 2, which is di, and then O is oxygen, and I have 5 of them, so my prefix would be penta. And then make sure I change the last 2 or 3 letters to IDE, so I have diphosphorus pentaoxide. So you try the next one. Alright, so we have 1 nitrogen and 3 hydrogens. We don't need to put the mono on 1 because it's first. So we have nitrogen trihydride. All right, now let's do the opposite. Nitrogen on the periodic table, what's the element symbol? Oxygen on the periodic table, what's the element symbol? Right, in O, we have 2 nitrogens because of the prefix Di, and we have 3 oxygens because of the prefix tri. So we end up with N2O3. I couldn't write those as subscripts, but you know they need to go down. You try the next one. Right. The element symbol for phosphorus is P. The element symbol for fluoride is F. And we have 3 fluorides, so we put a subscript of 3. Now finally try the last one. Awesome. The element symbol for silicone is Si. The element symbol for fluoride is F. So we have F, and we have 4 fluorides because of the prefix tetra. So silicone tetrafluoride is SiF4. All right, I'll see y'all next time.